Welcome to our webinar, Production of High Precision Pump Parts, Grinding Solutions from EMAG for Greater Efficiency. My name is Manfred Winkler. I am Head of Technical Sales for the business unit Grinding in the EMAG Group, and I will guide you through this webinar together with my colleague Yannick Röttger next to me. Before we start, a brief organizational note. If you have any question about the topics presented, you have two ways to ask them. Once via the chat function, your question will appear here with your name, or via the question function, your question will appear here anonymously. Yeah, what you can expect in the next 45 minutes. Here you see the contents. Basically, after a short introduction, we are prepared for three main points. The first is our small vertical non-round grinding machine VG110, where we will show you two applications. The second is our VLC series machining, the combination machine, also with two applications. And the third are informations about our EMAG Contour. This is the software for non-round grinding. Now we are coming, what was the motivation for this webinar? According to a study by Growth Market Reports, the global pump market is a growth market with an annual growth potential of around 4% until 2031. Pump systems are not visible at first glance, but very important components in a variety of applications in our daily life. You can find pump systems in cars, in commercial vehicles, in vehicles for agriculture, in construction, and you can find it also in household applications or in heating systems. The increasing demand of energy efficient pumps is likely to boost demand for pumps on the market. So therefore, the pump market is therefore an interesting market area which differ from other market areas which currently have stagnation or decline terms of growth. So that's the motivation for this webinar, and now I will hand over to Yannick for the first point, VG110. Please, Yannick.
Thank you very much, Manfred. Good morning, ladies and gentlemen. My name is Yannick Röttger. I'm responsible for the Department of Technology at Business Unit Grinding in Saarlach, and I'd like to introduce you in the next chapter our machine solution VG110, a vertical grinding machine optimized for the production of small parts with non-round geometry. I'll present two use cases, two applications that have been carried out together with our customers. The manufacturing of a pump ring, of a hydraulic pump, and next a rotor and stator of a steering pump based on a G-rotor pump system. The VG110, the workpiece portfolio includes workpieces up to a machining diameter of 110 millimeters. We can grind stators, rotors for G-rotor pumps. We can grind pump rings for vane pumps, which we will focus in the next minutes. We can also grind cam parts for camshafts. So a wide range of application. And as you can see, especially in correlation to the size of the manual panel, you can see it is a very compact machine with a small footprint, machine width with only 1.4 meters, so it requires very low space in your production shop floor. The core component of a vane pump is the pump ring, which is shown here. We grind the internal diameter, marked red in this sketch. And the quality of the contour and also of the surface finish has a significant influence on the energy efficiency and the noise emission of the pump in the further application in a vehicle or other machine types. So an optimized grinding process does not only save resources in your production, but also has a positive influence on the energy consumed in the further application. So we can optimize the holistic life cycle of this tool, of this part, and that's what makes the process design so interesting and challenging. What is the main functional principle of a vane pump? We have to understand this to make sure that we really achieve the required quality of the parts with regard to the further application. The red marked part in this sketch is the pump ring, which is ground with a non-round geometry in our grinding process. The rotary rotor is the yellow part inside, and the vanes are fixed in these notches here, and with springs there is a force that you have also material contact between the vane and the pump ring, so you have got fluid chambers with varying volume according to the ring geometry. In this video you can see on the inlet side we start with a small chamber volume, it gets bigger, so there's an inlet of fluid, and the fluid chambers then get smaller, so we generate pressure, and that's what makes the pump work. Here you can see it in steel. The pump ring is the part with the flat ground surfaces that we can see here, and the two holes for the inlet of the fluid in these sections. The rotor inside with the vanes is also visible here. What is our machining task for the internal grinding process of the pump ring? We have to machine hardened steel 100 chrome 6 or sintered metal D32. In both cases hardened, we have to grind the inner contour with a grinding allowance of 0.8 millimeter. So the main challenge in this task is to make sure that we get, after such a high grinding allowance, surface roughness lower than 0.2 microns. Of course, we have to pay attention to the shape of our part. The profile deviation has to be lower than 20 microns, the straightness deviation lower than 2 microns, and the perpendicularity lower than 7 microns. But focus here, achieving a surface roughness lower than 0.2. This is our machine concept. You can see the design and the orientation of the axis. This concept bases on decades of experience at EMAG with vertical grinding machines and machines for combination technologies. We have the machine base made of mineralite. The customer or his automation places the raw part at our workpiece shuttle and also takes the finished part from the finished position next to the raw part position, both in horizontal directions. The workpiece shuttle brings the part into the machine. It is lifted up by the workpiece lift. He is also responsible for the angular orientation of the parts, brings it to the clamping device at the workpiece spindle. The workpiece spindle moves in X direction and brings the part into the machining area. As you can see, we have two internal grinding spindles available here. They move in Z-axis direction, so they make sure that there is contact between grinding tool and workpiece. In case that we use vitrified CBN grinding wheels, which are dressed in the machine, we use a dressing spindle that is mounted on the workpiece spindle. On the right-hand side of the slide, you can see a system including also a workpiece handling system outside the machine provided by EMAG. How does it look in moving pictures? The workpiece handling here by our automation system brings the raw part to the shuttle, and here it takes the finished part from the shuttle. Here you see the placement on the shuttle, and here the finished part comes back for the further operation steps. Here the workpiece lift brings the part to the spindle, the grinding spindle moves in Z direction, and now the non-round grinding process can take place. As mentioned, we can use a rotary dressing spindle for the profiling and sharpening of our tools. We use it in combination with touch sensors based on acoustic emission signals. In this application, we use the dressing wheel diameter of 80 millimeters, and we can perform rotational speeds up to 16,000 revolutions per minute that we can set the process with the common ratios of dressing speed as required for vitrified grinding wheels. As already clarified, one important challenge, grinding a high stock allowance and simultaneously achieving a low surface roughness. So we've chosen a two-step grinding process. The strategy is to do first a non-round grinding of the pre-contour by electroplated CBN grinding wheel. Makes it possible to achieve high material removal rates. So we have a we have low times for the first step. The finish grinding process, after we made sure that the geometry is okay, we use then the finishing grinding process to make sure that the surface roughness is according to the requirements. For this we used a vitrified CBN grinding wheel, which is dressed in the machine. In both cases, the non-round geometry has been realized by an interpolation of the x-axis. This is the axis of the workpiece spindle, and the rotating of the workpiece in Z direction. For both processes, we used a grinding wheel diameter of 16 millimeters and a grinding wheel width of 20 millimeters. What is important to mention for internal grinding applications, we use an oil with a low viscosity, maximum 5 centistokes. Higher viscosity usually leads to an aquaplaning effect. We have a huge contact area between workpiece and grinding wheel. This can lead to high normal forces, which lead to form deviation of the geometry afterwards. So here viscosity quite low is required. What were the results of our grinding process? We achieved a cycle time, including loading and unloading, of 40 seconds for the part made of 100 chrome 6. And due to the better machining behavior of the sinter metal, we achieved a cycle time of 32 seconds. All in all, annual quantity of 450,000 parts per year has been realized with the following geometry quality. We have a straightness deviation lower than 10 microns, position deviation lower than 30 microns, perpendicularity was better than 5 microns, and the surface roughness lower than 0.2 microns. The next example for precision pump components are rotor and stator of a G-rotor pump, also known as internal gear pump. They are used as hydraulic pumps in many different applications. This part was desired for a steering system of vehicles from agriculture, but they are also used with a very high quantity in construction vehicles, in garden equipment, so many different applications that can be fulfilled by pump components like this. First, we have a look to the functional principle of this pump. You can see the increase of the chamber volume on the inlet side is realized by the relative speed between rotor and stator and their specific geometry. You can see the chamber volume gets bigger, so we have an inlet of fluid on the left-hand side, and now the chamber volume gets smaller, so there is a pump pressure generation on the right side. This makes it quite easy to understand why the focus in this case is mainly for the manufacturing of the shape deviations. We have to achieve very small shape deviations because they influence the efficiency of the pump. We have no vanes which can help to correct some form deviations here. The shape, the geometry really has to be perfect according to the requirements to have a high efficiency of this pump. For the rotor, we have to perform the outside grinding process for this part here, so outer grinding of the red marked area. The workpiece material was steel 20 CR TIC, hardened it up to a Rocknell hardness of 36. The external contour had a grinding allowance of 0.8 millimeter. The average surface roughness has to be lower than 0.5 microns, so a bit easier to machine than our last example, but as already explained, the position and the shape deviations are much more challenging. So profile deviation lower than 6 microns, parallelity lower than 12 microns, the perpendicularity has to be lower than 15 microns, and we have a very small angular deviation that is acceptable for the angle between the peaks of the polygon, also maximum 6 millimeter tolerance for the diameter. For the rotor, for the stator, we have to do the internal grinding process, same material, same hardness, slightly lower grinding allowance of 0.5 millimeters, and also the finish part has to achieve a surface roughness lower than 0.5 microns, perpendicularity lower than 50 microns, and the profile deviation lower than 10 microns. What was the general grinding strategy for this application? The first step, we did a pre-grinding process, then intermediate measurement with probe integrated in the machine, calculate the respective correction factors, and then do the finish grinding to achieve geometry and surface qualities. Same as in the last use case, non-round grinding by an interpolation of X and ZXs. In both cases, we used vitrified CBN grinding wheels dressed in the machine. The angular orientation has been done on the workpiece lift, and then in both cases we had actual clamping according to the angular position of the internal gearing or the inner contour for the stator. Because of the geometry and especially the contact arc between grinding wheel and workpiece, we could use a grinding wheel with a diameter of maximum 16 millimeters for the rotor, but only 7.4 millimeters for the stator. We have got less accessibility for the grinding wheel. We would have contact to both surfaces, so the diameter is very limited, and this leads to very difficult ratios of length and grinding wheel diameter, which makes it very difficult to find optimized process parameters. Again, we use an oil with a low viscosity, as already explained, and the results in this example for our customer, we achieved a cycle time of 110 seconds for loading, unloading, intermediate measurement, and the both grinding steps. The stator required a cycle time of 120 seconds. In this example, we used the grinding wheel width of 26 millimeters, which was just a bit bigger than the width of the workpiece. In case that we have different workpiece geometries with smaller workpiece width, then of course it is possible to clamp them as a package in the machine. We can handle with a total width of grinding of 35 millimeters, so for some applications even higher. This always depends on the geometry of the parts, if we can use bigger grinding wheels, then of course we can increase the width of the grinding tool as well. Finally, we achieved straightness deviation lower than 6 microns for the rotor, lower than 10 microns for the stator. Perpendicularity was lower than 10 microns, respectively 15 microns, and in both cases the average surface roughness was lower than 0.5 microns. You can order the machine, of course, for manual loading, or in case that you want to link the machine to your own workpiece handling system. In this case, the shuttle is the connection to all the other steps. All the rest of the workpiece handling inside the machine, angular positioning, clamping, bringing it in the contact zone in the machining room, all this is done by the machine. And of course, we also provide workpiece handling systems for the automation, which are constructed and produced by EMAG. Finally, I'd like to summarize the main features of the VG110, optimized for small workpiece geometries up to 110 millimeters. We have a high vibration damping thanks to the mineralite machine base. This enables us to achieve long tool lifetime and also high surface finish quality. The chips can fall down into the dust collector. We reduce the interaction between abrasive parts in the grinding dust and the machine axis to a minimum. We have short chip-to-chip times because of the automation by means of the workpiece shuttle, the lift, and the pickup spindle. The machine is very small, so requires very low space in your production. You can place the machine on very small spaces, and we have a very good accessibility. If you open the front door, you have a good access to the clamping device, to the two grinding spindles. You can observe the contact zone very well. This is very good for setting up the process to other workpiece geometries.
So, thanks, Yannick. Before we come to the next chapter, we have already first questions in the chat. The first question is, which raw part quality is important when machining pump rings?
As usual for a grinding process, it's always an advantage if the input geometry is very close to the finish geometry, so we can reduce the grinding allowance. We can switch to a single-step grinding process and achieve a lower cycle time. But this always depends on the whole process chain, which is usually fixed by the customer. Of course, to achieve a good perpendicularity and low shape deviations, it is important that the reference surface, which has contact to our clamping device, has a very good quality, a very low flatness. So usually there should be a double-side grinding process before to make sure that parallelism is according to the requirements.
So there is a next question. What is the minimum quantity for an automated machine?
The minimum quantity that an automation makes sense. This question is, of course, hard to answer in general. So we kindly invite you to contact our colleagues at the Department of Technical Sales. They are the experts to make sure that we've got all the information from customer side, and then we can do a good approximation of cycle time, and then together we can decide if an automation makes sense. This, of course, depends on the workpiece geometry, on the labor cost, and of course on the investment costs for the required workpiece handling system. But this we can of course discuss in detail if you contact us.
Thanks. There's another question. Pump components have a very different geometries. How can a quick retooling of the machines be ensured?
I think I already mentioned it. We have a very good accessibility because of the big front door and the vertical spindle layout. Everything is just in front of the operator. It's easy to change the grinding tools and also to adjust the clamping device. I think one big advantage is that 2 grinding spindles are available. As shown in the last example, we can set 1 grinding spindle for the production of the rotor, one for the stator, and this makes it quite easily to fulfill the requirements for 2 different geometries. So I think this is also one advantage of this machining concept.
Okay, there is one more question. Are only CBN grinding wheels used in the machine, or is it possible to use corundum grinding wheels as well?
Yeah. In general, of course, you can also use corundum or other conventional grain material wheels in our machine. But as we have to deal with very small grinding wheel diameters, we have just a small number of grinding grains which have to do the machining work. So there's usually much more wear than you know from bigger grinding wheels. So it makes sense to use super abrasive grains, and in case of the machining of steel, of course CBN makes sense. CBN has 2 other advantages for internal grinding. In internal grinding, we have a high contact area between grinding tool and workpiece. So usually there's a lot of heat generation. And CBN grinding wheels, because of the split ring behavior, they always have small sharp cutting edges. So this reduces the temperatures in the contact zone. And also CBN has a much higher thermal conductivity, so heat can flow in the grinding grain, in the grinding tool. This also reduces the temperatures in the contact zone. And one additional information, as we're talking about temperatures in contact zone, makes it very important to pay special attention to the coolant supply. Usually we use, in this case, CBN grinding wheels in combination with 3D printed cooling nozzles.
Yeah, a question which coming in each webinar. How long is the lifetime of the tools? How many pump rings can be machined?
Okay, yeah, this is really the standard question in our webinars. Unfortunately, not possible for me to give a precise answer to this, but we have a lot of information in our data. We can do a good approximation of grinding wheel wear if we know the workpiece material, the workpiece geometry, the required cycle times. So this is a question that can be very good discussed in more detail if you contact us or our colleagues.
Okay. So thanks for answering these questions. Now we come to the second chapter of our webinar, VL series. We will show you 2 applications on these machines. You know, the VL series are the machines which are very flexible, where you can use many technologies inside. So one application we will show you, it's a non-round grinding application for a housing integrated cam ring, which you can find in radial piston pumps. And the second application, it's a combination machining, grinding and brushing of a control plate, which you can find in the axial piston pump. So here on the right side, you see the workpiece. It's a housing integrated cam ring. The size is much bigger, like the parts which we discussed before. And here inside in this cam ring, many pistons are moving up and down to realize the suction and the pressure function of the pump. Here we have a small animation. The contour of the cam ring determines the radial stroke movement of the pistons, which result in a constant volume flow on the pressure side without any pulsation effect. So let's have a look for the workpiece details and the machining requirements. Here on the dimension you see already, these are much bigger parts. The OD is 232 millimeter, the height 108 millimeter, and the weight is 16 kilogram. So that's a very heavy workpieces. The material is hardened 50 CRMO4, hardened to 58 to 63 HRC, and the areas which we have to machine are marked red. You see here first the inner contour, then we have to grind the face, and we have to grind also the OD. The grinding allowance in the inner contour is 0.8 millimeter in diameter. That's still a big stroke if you see the length of the chem contour. The requirements for the quality, the surface quality is RA 0.4, and the contour line quality is 50 microns. That's really a high request. We have a straightness of 5 microns, and the perpendicularity between the inner contour and the face what we grind is 20 microns. So on which machine concept we realize this? This is on our VLC 350 GT. This is our standard combination machine, which is very flexible. On the right side, you can see a standard picture, the machine equipped with a turret for turning tools, a ID spindle and a OD spindle. But for this application, we modified the machining area inside with 3 grinding spindle. Basically, the machine bed here is also made of mineralite, like what we heard before on the VG110. And the big advantage here is inside on this machine bed, you can put many different technology units to find the best combination, and you can set up the workpiece in one clamping and get highest quality. Here you see the machine, the x-axis on the top. The x-axis bring the workhead from the loading area in the machine inside and back for the unloading. We have the vertical z-axis to pick up the workpieces, and here inside in the working area we have 3 grinding spindles, and here we have really 3 different grinding process: non-round grinding, round grinding and face grinding in one machine. Let's have a look for the grinding process, the grinding chain. The first is the grinding of the inner contour. It's a non-round grinding process. It's the interpolation between the x-axis and the z-axis, and we are used vitrified CBN wheels. The second step is the grinding of the face. Here also we used vitrified CBN grinding wheels, but we used a special specification that this wheel can be self-sharpened. This means there is no dressing necessary for this CBN grinding wheel. And the third grinding operation is the grinding of the OD. It's a cylindrical grinding process, and we did this in a pre-grinding, intermediate measurement, and a finish grinding, because the request was to reach a tolerance less than 10 microns in the diameter. Also here we used CBN, vitrified CBN grinding wheels. Here we can see the results of this application, cycle time and quality. The cycle time was 440 seconds, including the loading and unloading time. We used oil for this application. And interesting is here, before we saw on the VG110, the wheel diameters are approximately 16 or 20 millimeter. Here we can use a bigger wheel for the contour grinding because we have a bigger chem contour. It was here diameter 40 millimeter, but this grinding wheel is always calculated to the minimum radius of the chem contour. We reached the requested qualities. The line shape smaller 50 microns, the straightness smaller 5 microns, perpendicularity smaller 20 microns, and the surface finish quality of RA 0.34. So now we see a small video of this application. To here the machine, the VLC 350 GT, the front view. This machine is equipped with a O conveyor type with pellets for raw and finished parts. We pick up the raw part with a clamping arbor in the bore. Then here we have to do a pre-radial measuring in the reference hole because the inner contour must have a relation to this reference hole. Now we see in the first step grinding of the inner contour, the interpolation between X and Z axis. Then we have in the second step the face grinding. As I mentioned before, here we use a special CBN specification, a self-sharpening specification. This wheel must not be dressed. And the third operation here, it's a pre-grinding of the OD. Then we have the measuring of this OD. Then we know the exact stock what we have, and the last grinding process is now the finish grinding of the OD. After the grinding process, the part is unloaded on the pallet of the conveyor system again. Good. The second application, what I want to show you, this is a control plate, which you can find in axial piston pumps. The material of this control plate is a hardened HCrMO16, and what we have to grind, it's marked again in red color here. We have to grind the face, we have to grind the OD, and we have to grind the sphere. As you see here, we have to grind on both sides. Therefore, it's necessary to make the grinding in two steps. In a first step, then we have to put the part out of the machine, turn it 180 degrees and bring it inside again for the second step. The grinding allowance on the diameter is 0.2 on diameter, the face 0.1, and on the sphere we have 0.1 in radius. Special here, I want to show you the requested quality. The surface quality of the sphere is RE 0.1, that's a hard request, and also the area form error of 4 microns and the runout of 20 microns to the basic A and B, which is the face and the OD. So the machine concept, basically, it's also a VLC machine, but it's a smaller size. It's a VLC 200 GT. It's a smaller system of the VLC 350 GT, what we saw before. On the upper side, we see again the X and Z axis. We see the workhead with the clamping system and with the dressing spindle. And on the machine bed here are assembled 3 spindles. On the left side, you see the inclined positioned grinding spindle for the OD grinding. In the middle, you see also an inclined positioned grinding spindle for grinding the sphere. And on the right side, you see a motor spindle. This motor spindle is equipped with the brush. Now we can see here the details of the process chain. First, we start grinding with the face. We are grinding with a corundum wheel, diameter 400 millimeter. For grinding the OD, we are using the same grinding wheel. And then afterward, we make the brushing process with a plastic brush with abrasive grit. Why we have to brush here, the request on the drawing is it's not allowed to have any small burrs on the edges of the workpiece. Then we move with the workhead the part out on the shuttle, turn it with an external turnover unit 180 degrees, clamp it again in the bore and bring it in, and then we have to grind the sphere. This grinding process we do with a cut wheel with diameter 60, and the specification, it's a resin bonded silicon carbide wheel, and the last step is again brushing the opposite side with this plastic brush. Here we have a very nice view in the machining area. On the left side you see on the top the clamping system and the workhead, and on the bottom on the left side you see the incline grinding spindle for the OD grinding. In the middle you see the spindle for grinding the sphere, and on the right side we have the motor spindle with the brush. For this application we use two different dressing units. For dressing the OD grinding spindle we are using a rotating diamond form roller to dress the face and the OD of this wheel. And for the cup wheel we have to use a fixed single diamond dressing tool to dress inside the cup form, because here inside we cannot go with the big diameter of the rotating wheel. This is not possible to go in, therefore we use this fixed single diamond dressing tool. Yeah, which cycle time and quality we reached? The cycle time was 3.82 minutes, including loading, unloading. We are using emulsion for the grinding process, and let's concentrate on the qualities what we reached on the sphere. The shape form, really, we reached smaller than 4 micron. The runout was smaller, like 5 micron, and the face quality was smaller, like RA 0.1. Interesting application. So now I want to give you more information about this VLC series. With this machine, basically with this pickup machine, you get the automation included, because the workhead is moving from the loading position the part in the machine, then you have the machining and bring it back for unloading. So this automation cycle is already included in the machine. And we can offer you basically two options for the automation. On the right side, on the top, you see the machine with a shuttle automation. The shuttle automation move forward and backward in the loading unloading area. And outside the machine, such a shuttle normal will be load and unloaded via automatic cell. On the bottom side, you see the VLC machine with a O-belt automation. It's running around here, and on this conveyor you can have up to 20 pallets for the parts, and most time this conveyor is loaded unloaded manual by the operator. Here are some examples which technologies can be used in this combination machine to reach the best quality. You can do hard turning, skiving, internal grinding, external grinding, cylindrical grinding, non-round grinding, honing, or also brushing is possible in the machine. So here I want to make a summary of the advantages of this machine type. It's possible to make a complete machining in a single setup. This brings a maximum of workpiece accuracy. As it's possible to combine different technologies in the machine, like turning, grinding. Here you can use round or non-round grinding, what we saw, milling, reaming or honing. This is a very big advantage for this machine type. You have the integrated automation as showed. We have short distances and therefore the time, the chip to chip time is very short. Here we have the typical EMAG vertical machining. It's the best way the chips fall downwards. We have a small footprint because we can do many technologies in one machine. It's not necessary to place in your workshop one turning machine and one grinding machine. You have only one machine, so you have a small footprint, and your operator, it's possible to have a multiple machine operations. Then we have a very good accessibility in the machining area to change the clamping chucks to change the grinding tools and the dressing tools. So that's really perfect. And if you have many machines of the wheels in your workshop, you have identical basic machines. And this is standardized operation and part programming. So that's the end of the chapter 2.
Yeah,
and
so before we proceed, we will try to get in discussion with our audience. We have some questions in the chat. First question, very good remark, because we already discussed it in the German version of the webinar. Why is the diameter of the outer grinding wheel so small?
Yes, basically this cam rings in the housing, the customer has two different types. One type is for the inner contour with a surface quality of RA 0.4 and one of RA 0.2. If the request is for RA 0.2, we saw already in the presentation, in your presentation on the VG 110, it's a two-step grinding process. This cannot be done. A stock of 0.8 millimeter in the diameter and you grind only with one wheel. One wheel is selected to grind the material away and the second wheel is selected to make the cam contour and the surface quality. And therefore it's the reason we have two small wheels inside, and we use now the possibility, if the surface quality is requested RA 0.4, use this second small wheel for OD grinding operation.
Okay, there are some more questions. Do you use grinding cycles or do the programs have to be written by hand?
Yes, sure. We have fixed standard grinding cycle and dressing cycles. Grinding cycles like incline grinding of faces, OD grinding, or dressing cycles also for dressing the face and the OD. These are standard cycles. Sure, to make the complete NC program, you have to put together these grinding cycles together with the geometry data, the dimensions of the machine, and the detailed grinding process data like cutting speed or infeed and other things.
Next question deals with our measurement system. Is an intermediate measurement of the diameter always necessary? Is it not possible to simply measure in cycles?
Yes, the first question is it not necessary that you have always measuring for each part? That's right. Only for this application to reach a quality of 10 microns in the diameter, for this application we measure each part. Other things, we have a standard cycle to measure each 10 or 50 parts. It's not necessary to measure each part. That's right.
Next question, also same topic. What measuring tasks can the integrated sensor perform? Is it possible to integrate an external measuring system to make process corrections if necessary?
Yes, the integrated measuring probe we use basically to set up a process, a grinding process, to make already the first part in quality. Then we have a pre-machining, a measuring, and then we make the final machining. This ensures that already the first part is in quality. And it's no problem to combine the machine with an external post-process measuring machine or unit. This we did already many times. And then basically the measuring data are coming from the post-process measuring machine to the machine. And we are using this to get constant quality all over the day.
Okay, no more questions so far. So we will proceed with the next chapter, short chapter about our software tool for non-round grinding called EMAG Contour. As we have to deal with very complex geometries where we need a very good adjustment of two machining axes in correlation to each other, the rotation of the z-axis and the linear feet of our x-axis, it is very important to take into account the dynamic behavior of the machine to make sure that the geometry of the ground part is in accordance with the required geometry data from the customer. EMAG Contour uses the geometry data from the customer as input and calculates, because it knows the dynamic behavior of our different machine types. Based on this data, we calculate the most productive grinding parameters with regard to cycle time, but make also sure that we avoid any upswinging effects because of the movement of the different axes. We have to make sure that there is a very smooth path of the grinding tool to make sure that the geometries are according to the tolerances. We can also use eContour to calculate correction parameters, because we can also implement the data from the measurement in eContour and make sure that we get the correct NC data with regard to position, way, speed and acceleration from the different machining axes. So finally, I'd like to summarize the content of our webinar on high precision pump parts. We have seen that the pump market will grow in the next years, because pump components are not only used in automotive sector. We have a wide range of applications in construction, agriculture, vehicles, but also in consumer parts and so on. So we have many applications and high request of the respective parts. We have shown that we offer specialized machine solutions depending on the part geometry and depending on the technologies that are necessary to machine the parts. The VG110 is optimized for smaller parts up to a diameter of 110 millimeters, optimized for internal and external grinding of non-round materials. The VLC series can also be used for parts with bigger dimensions, with bigger diameters and higher workpiece weight. VLC series makes it also possible to integrate other fine machining technologies, hard turning, brushing or honing, and so the VLC series is a very flexible machining concept for the processing of chuck parts. EMAG Contour, our software tool, helps us to generate the correct NC data for different geometries, always with the objective to have a short cycle time while fulfilling the quality requirements. So, to come to an end, before we start in the last round of questions and discussions, I'd like to introduce you to the Grinding Hub exhibition next week in Stuttgart. We will be in Hall 9, booth C31. We present there the VTC 100 GT, a combination machining concept for grinding and other fine machining for shaft components. We will present our VLC 450 DG, our machine for the double-side grinding of hard-coated brake discs. We will present the two machines of our V11 series, universal grinding machines. So many things to find out about EMAG, and a very good possibility, a very good chance to get in contact with us to discuss your grinding tasks with us in more detail and personally. So we would be very happy to meet you there. Kind invitation to the Grinding Hub next week. To come to an end, we will now have a final look in the question chat. Manfred, there's one question regarding the maximum workpiece size. So what is the maximum workpiece size that can be machined on the VLC 350?
Yes, you can see this already in the machine type. The maximum diameter is 350 millimeter and the maximum workpiece height is 200 millimeter. And as we saw also the VLC 200, the application for the control plate, maybe I want to mention the maximum diameter on the smaller machine. We have the maximum OD of 160 millimeter and the maximum height of 100 millimeter.
Is it also possible to machine shafts between centers on the VLC machine?
No, that's not possible. This machine type VLC is designed for flange parts. We have no tailstock in the machine, but you mentioned we will see on the grinding hub already one machine series. It's a VTC. On this machine we can turn and grind shafts because this machine is equipped with a headstock and a tailstock for clamping the shafts.
Yeah, I think there are no more questions in the chat. Nevertheless, of course, you can contact us directly if there are more upcoming questions after the webinar. We are always happy to discuss the problems personally with you. Thank you very much for your attention. We will find the webinar also in some days in our media center, so you can have one more look about the things that are relevant for you. You also find there a lot of information about the other machining technologies that are provided by EMAG, so many things to see there. We would be happy to meet you at the grinding hub and say once again, thank you very much for your attention.
Also from my side, thanks to join this webinar and bye-bye.